Okay, Unit 4, Day 2, just a quick warm-up of solving exponentials, and then we'll get into some applications of exponential problems, which is kind of what you're going to encounter as we go on through the unit. All right, so this first one, we need to isolate the exponential piece, so I'm going to add 13 to both sides. And that's going to be 24. Once I do that, I can change to a logarithm. So log base 3 of 24 equals 5x plus 2. Solve for x, use your calculator one time at the end. Don't start calculating and rounding as you go. So I'm going to subtract 2. So negative 2 log base 3 of 24. Divide that by 5 or multiply by 1 equals x. There's the exact answer. If you use your calculator one time correctly, you should get about 0.179. So again, if you don't want to use the fraction key, just calculate the numerator, press enter, and then take that answer divided by 5. Remember how to get log base 3 of 24. You have a couple options. Alpha F2 will bring up log base, or you can press the math key and arrow up or down until you get to option A, which says log base. Okay, so for this one, it's going to be easier to notice that both of these numbers have the common base of 7. So 1 over 49 is equal to 7 to the negative 2. And then I have negative 4x plus 5 as my exponent. 343 is actually 7 to the third. And I have my exponent of 2 minus 3x. So now that I have my same base, I can use my power of power properties and just set my exponents equal to each other. So if I take negative 2 times negative 4, I get 8x minus 10. And I'm multiplying by 3 here, so I get 6 minus 9x. Gather my x's, move my constants, so I get 17x equals 16. So x is equal to the exact value of 16 over 17. All right, there's a quick review of those. Okay, so we're going to look at some applications of continuous growth and decay. So here's your basic formula. So A, obviously, on the left side is your final amount at a certain time or after a certain amount of time. A sub 0 is your initial amount. T is obviously time. Pay attention to the time frame. And K is your growth or decay rate. As a decimal. So if K is greater than 0, it's a growth. If K is less than 0, it's decay. Okay, so example number 1. There's a population of bacteria that grows 17.4% per day. There's my growth rate. There's 20 million at the start. There's A sub 0. How much will there be after 15 days? So this is a pretty basic one. A sub 15. And there's no reason to put all the zeros. Just remember your answer is going to be in millions. So I'm just going to use 20 here. E to the 0.174 times 15. So A sub 15 is about 271, and we usually go thousandths, 0.981. Make sure you label that millions. So that million is the key. So that one was very, very basic. All right, so some chemistry now. Carbon-14 decays at a rate of 12.3% per 1,000 years. The current mass is 322 milligrams. How long will it take for it to decay to 100 milligrams? Okay, so my initial amount is going to be 322, and I'm going to set it equal to 100. So remember that decay is negative, so I need to use a negative 0.123 because it's a decay rate. So I have 322 milligrams E to the negative 0.123. I don't know my time, but I do know my time is every 1,000 years, and I'm going to set that equal to 100. So I need to isolate the exponential piece. Divide by 322. Since you're using your calculator, just leave it like that. There's no reason to change it to a decimal, and when you start rounding numbers, then your answer gets off. So now I can change to a logarithm. This is log base E, so I can do natural log of 100 over 322 equals negative 0.0123 times t. Now I'm going to divide, so I get natural log of 100 over 322 divided by negative 0.0123 equals t. Make sure you get your calculator, make sure you have it. Put that value in your calculator and make sure you're getting the right answer. If you have trouble with your calculator, you're going to need to ask me in class. You should get 9.507. But remember, that is thousands. So always label your answers. Okay. The population of snail bots. If you want to know what a snail bot is, you can Google it because you will get some hits, I guarantee it. So snail bots on the planet Dorbrion grows at a rate of 4.1% per year. Currently, the population is 4,000 snail bots. I want to know how many snail bots there's going to be after 3 years, and how long will it take the population to get 7,500 snail bots. Okay, so A is pretty easy. I'm just looking for A of 3. Equals, my initial amount is 4,000. E, my growth rate is 0.041 to 3 years. So A sub 3, if you calculate it correctly, is 4,523.538 snail bots. I'll leave it as a decimal. So for B, I'm just going to take the same equation, but I'm going to set it equal to 7,500 and solve for T. So 4,000, my initial amount, E to the 0.041 times 3 equals 7,500. Oops, I don't want 3 there, I want T, I apologize. So 0.041 T. So if I divide by 4,000, I get e to the 0.041 T equals 7,500 divided by 4,000. You can leave it just like that since you're using your calculator. So now this is another natural log. So I'm going to go ahead and cross off my zeros. So I get 75 over 40 divided by 100 when I cross those zeros off equals 0.041 T. So T is going to be the natural log of 75 over 40. Make sure you close your parentheses when you do this. Divided by 0.041. And I came up with about 15.332 years. So remember, if I'm going too fast, you can pause this video anytime and go back and watch a piece that you missed, or just pause it and catch up with your running. Okay, so let's see. Where am I at here? I already did the snail box. Now I'm on Planet Mathtopia. Do I have another one back here? Oh yeah. We're going to do this one first. And then I'm going to go back and do the other one. So let's do the magnesium one first. Okay, so there is 165 grams of magnesium 27. After 9.45 minutes, there is only half the amount left, which is 82.5. What's the rate of decay? So remember, I should get a negative value when I solve for that exponent. All right, so my current is 165. My final is 82.5. And it's after 9.4 minutes. So A sub 0, or my initial amount, is 165. K is my unknown. And A sub 9.45 minutes later is 82.5 grams. So if I set my equation up, I have 165 E to the 9.45 K. I'm solving for my growth rate, so K equals 82.5. So if I divide, I get E to the 9.45 K. And I knew that it was half the amount. I can use 82.5 over 165, that would be fine. But I also know that that was half because it was told to me in the problem. So now I can do natural log of 1/2 equals 9.45 K. If I divide, I'm going to get my growth rate. It should be negative. I got negative 0.073, which shows me it's a decay. So it decays at a rate of 7.3% per minute. All right, so back to Planet Mathtopia. Okay, so Planet Mathtopia, radioactive isotope of netium-55, decays at a rate proportional to its amount. Initially, there is 477 grams. After 15.4 thousand years, there is 340 grams left. I need to find the decay rate, and then I need to find out how many years, how much will be left 20,000 years from the beginning. Okay, so sometimes on these are going to start getting a little complicated. It's kind of interesting just to do a little timeline. So if I put my initial, can't spell today. So my initial was 477. So that's my A sub 0. And then after 15.4 thousand years, so into the future, I had 340 grams. So that would be A sub 15.4. Okay, so you got to pay attention to the wording on these. We'll do more in the next couple days. Okay, so for part A, I just have to find the decay rate. So my later amount is 340. My beginning amount was 477 grams. E, and I need 15.4 years times K. So I have 340 over 477 equals E to the 15.4 K. I have a natural logarithm. So 340 over 477 is 15.9 K. Actually, it's 15.4. My apologies. Should be 15.4. So if I divide, over 15.4, I should get a negative value for K since it is a decay. So I got about negative 0.022. So this decays 2.2% every 1,000 years. Okay, so now I need to know how much would be left after 20,000 years from the beginning. So I want to make sure that I use this 477. So A sub 20, remember that's 20,000 years, is 477E to the negative 0.022 times 20. Make sure you use that decay rate as negative. So I got 307.205 grams after 20,000 years. Not too bad, just read carefully. Okay, so one final one. Not a lot of information here, but a lot of calculations to do. So it's going to take 9.4 million years for 720 grams of nerdium-13 to decay to 4,000 grams. How long will it take to decay to 275? So the first thing I have to do is figure out my decay rate. So again, a timeline. Now I have 720, if we think about it like that. 9.4 million years I had 400 grams. And how long will it take to get to 275? Okay, so the problem doesn't really tell us, do we want to know how long it's going to take from the beginning to get to 275, or how long it's going to take from currently, or the 9, or this one right here. So we'll go ahead and do it from now. And I can talk about if they would have been a little more specific if they wanted to know from today, which would be the 400 grams. All right, so the first thing we have to do is calculate our decay rate. So I know I have 400 grams, 720 E to the 9.4 K, because that's my time. So we should be getting a little quicker at this by now. So I need to take my, oops, I forgot my E. So I need to take my natural log of 400 over 720. I know I'm going to need to divide by 9.4. That's going to equal K. I get K as negative 0.063. So that's the K rate of 6.3% per million years. So now again, I'm just going to go from the beginning. So I'm going to go to 75. That's what I want to know. My beginning amount was 720. E to the negative 0.063 T. So 275 over 720 equals E to the negative 0.063 T. So I know I need a natural log. Divide by negative 0.063. And I should get my time as being about 15.277 million years. From the beginning. If it would have asked for how long will it take from today, the process is exactly the same, except you're going to start with your 400. So you would have had 275 equals 400. E to the negative 0.063 T. If you just kind of look at the process, everything's going to be the same, except instead of over 720, it's going to be over 400. 275 divided by negative 0.063 T, or negative 0.063. So here you would have got T as about 5.948 million years from now. So read the problems carefully so you know where you're starting from. If you kind of go back and just look at this one, this is from the beginning. Well, if you take your 5.9, say, from now, and add the 9.4 million years, then you get about the same answer as 15.3. So there's a few ways to do that. Just make sure that problems will be more specific, so make sure you read them carefully. All right, so that's the end of growth and decay. Next up is going to be Newton's law of cooling. So something to look forward to. Have a great